Hello, everybody. Adam Lusek here, and today we're going to be talking about artificial intelligence agents. And while they might not be as exciting as, this guy right here, you've probably heard a lot of the hype around things like Devin, the all-in-one chat AI agent that can simplify your life and will write code for you, surf the web, do a lot of things that regular language model flows and just regular prompting of language models can't actually do on its own. Few other good examples that I've seen are things like Chat Dev, where they've even got this great visualization of using multiple language models with somehow the seeming ability to do stuff, things like coding, designing, testing, and they're all working in tandem together to sort of produce one final output. Their example here is, develop a Gomoku game. It goes here to the Chat Dev studio, and then it comes out with code and documents. Sounds wonderful. Other things that you might have seen, stuff like AutoGPT, the streamlining of building AI agents, and even Microsoft themselves have gotten to stuff like AutoGen, where you're seeing this, maybe some confusing diagrams to you if you're not super into the artificial intelligence world of, a user that has then a commander that goes to a writer and a safeguard and, next generation LLM applications. How does this work? So that's what we're going to be going into. So NVIDIA has this wonderful blog post here of an introduction to LLM agents that I'll have linked down below. And their sort of overarching definition for it is a system that can use a large language model to reason through a problem, create a plan to solve the problem, and then execute the plan with the help of a set of tools. And so I really like this figure here that they've got here. You've got the user request going in, and then you have this agent core. And the agent core is what the actual, large language model is. It then has things like memory, planning, and then tools that it can use. So we'll go into what sort of all of those actually mean. But before we get into the actual practical examples, I would be remiss if I didn't bring up the React Synergizing Reasoning and Acting in Language Models paper that really sparked a lot of this advancement in the agent space. And so they realized that taking a look at things like early LangChain applications, where you would break down a problem into smaller steps and then do either, one shot, zero shot, or few shot prompting to get a more robust output at the end, you can actually model this a little bit using language models to sort of simulate how we as people approach problems. So their sort of proposed thing up here, to break it down a little bit more simply, is that when approaching a problem, you first go through a reasoning stage where you break it down into subsets and then think about all of the different things that you actually need to do to approach this problem. And then only then, at those specific points of what you actually have figured out what you need to do, you take the actions and use sort of your environment and anything available to you to attack that problem and get that final output. So if you combine that together into sort of a reasoning and action architecture, you can put a language model in the middle, have it reason through a problem, and then take actions on those, and then do this feedback loop a few times to get that better output using the language model as almost a, chain of thought reasoning application. And so one of the things people started to realize too that would help with this is that language models really don't technically, know anything. Their internals are all just, biases and weights and things like that that are fine-tuned as hyperparameters in the training of all these machine learning networks, yada yada, all that fun stuff. But at its core, they don't actually technically know anything. And you can see this because if I ask, what is the weather today in San Francisco to GPT 3.5, it says, sorry for the inconvenience. I don't have real-time capabilities such as accessing the internet or providing current weather updates. You should do this yourself. It doesn't know anything. It doesn't have any actual, knowledge within it or memory within it. It's purely just a generative predictive model. But if I move over to GPT-4 and I ask what the weather today in San Francisco is, you can see that it actually gives me an example. But it doesn't actually know this. It says here that it got this from the National Weather Service website here. So this really brings out a crucial thing that's been happening recently, the idea of using tools and function calling with large language models. And function calling is really the best approach that we've seen to sort of solving this problem of the language model not actually having any intrinsic knowledge. It's able to use sort of different tools that can be defined by you to actually get the current information and understand when it needs to use that current information to actually give you a more accurate output for your input. So what we saw here is things like, get current weather that ChatGPT uses. Other things can be, things like converting natural language into API calls, structured data from text, and pretty much a whole lot of other things. And the really cool part about this is that the language model actually reasons within itself, and we saw ChatGPT do this. So under the hood, when I say, what is the weather today in San Francisco, it knows that it's not going to be able to give you the accurate weather, that it needs to use the tools available to it to actually do this. And so one of the explicitly defined tools that must be under the hood for ChatGPT when we're using GPT-4 is searching the web and getting information from web searches. So it's actually able to do that, use that information that it finds on the web, and then give me this phenomenal, accurate, up-to-date answer. I can also ask something like, what is a good Wikipedia article to learn more about SF? And after it thinks for a little bit, it might even link it. There you go. See? So things like this, it wouldn't be able to, a language model in and of itself wouldn't be able to actually find those real-time data, do anything like that. But since it has under the hood this tool available to it, and it knows that it should be using this to get the most accurate information, it can actually call that tool, which is like an external search tool, to get that information before giving me the final output. The OpenAI platform itself has a couple tools built in that you can actually call, things like a code interpreter that allow an assistant or an agent that you're creating to understand when it needs to write and run code, and then can actually do that within its own environment, execute the code, and send it out to you. That's similar to how, if you ask ChatGPT to write you some code, if you're into the development stuff, it'll write the code, and then even if you're doing things like asking it to execute on maybe a script that modifies an Excel document, it'll be able to run that in its own virtual environment in the back end and then give you that final output. So it has things here like, code interpreters, and then they even have their own sort of RAG setup here where you can upload files, and then part of it will be a retrieval tool. And these tools can really start to be anything that you want once you get into the nitty-gritty of it. Of course, the people over at LangChain are quick to provide sort of the necessary infrastructure to start easily making things like this. And so some of their examples here include things like the Tavili search results tool. And you can actually make sort of your own tools and see how these tools come into play. Tavili search results is an external service, an API that you can actually input sort of just a plain string of text, and then it'll return some end results of just a simple Google search. And so that's one way of actually approaching and making a tool and being able to create a sort of agent now at this point where the agent has these tools available to it and can reason through and know that I should be using a search result to get better information for this question. And the most intuitive way that I like thinking about this is with this quick example. And I know I'm no artist, but bear with me for a second. The sort of before pre-agent stage, a base large language model, I feel is like, if you ask someone with absolutely no tools and nothing around, it's just the person, a plank of wood, and then a nail. And you say, hey, drive in this nail. The language model is kind of like that person. It doesn't really have anything that can help it do it. It can only use sort of what it has, what it knows, which is those internal weights and biases that make up the actual predictor within it. And so if it attempts to drive in that nail into the piece of wood, it's not going to do a great job. It doesn't have anything around it. It doesn't have, anything. This guy's, he's looking pretty sad. He doesn't have anything that can help him actually perform this task. He can give it a good shot, but the output that he gets actually putting the nail into the wood, you can see it's kind of sticking up there a little bit. He didn't do too great of a job. But moving over, let me get some, there we go. Moving over here, an agent is more when you take that language model and then give it sort of some basic reasoning skills and then also tools available. Taking the same example, if I asked an agent, this LLM here, hey, let's drive a nail into this piece of wood. And then also over on the side, there's a hammer here. But I don't necessarily tell him what to use or how to do it, the agent will go through a little bit of a process and be like, okay, I can't myself drive a nail into this wood, but here's a tool available for me to use, this hammer. So it'll intrinsically know, just sort of as we would if we were in the same situation, oh, I should just use this hammer because I'm going to get exponentially better output here. And so it uses the hammer, drives in the nail, gets great output, and everyone's happy in the end. And so that's sort of a very high level abstraction of thinking about the transition from just the base language model and prompting a language model to then creating an AI agent that has a little bit of reasoning skills that you sort of hard code in, and then tools available for it to use that it can reason and actually know when to use the tools to get that better output. But enough yapping about what agents sort of are and how they operate. Let's get into some actual real examples. And the folks over at LangChain have put together this phenomenal additional package, LangGraph, which basically is a framework for building agents as sort of state graphs, having some sort of internal agent that acts as a node, and then you can sort of more robustly connect these nodes of different agents together with edges so that you can specify exactly who can talk to who, how information is passed through from agent to agent, and then also it does all of sort of the automation of putting together sort of a message system and a memory system behind the scenes so that you don't necessarily have to do all of that hard work when putting together an agent. And so there's plenty different ways to set up different agent architectures, and LangChain has a phenomenal series of videos that you should go through if you really want to get down the nitty-gritty of different applications, different architectures of agents, and different ways of setting them up. I'll link it in the description below as always, and a lot of the code that you're going to see here is code that I've taken from those videos and sort of augmented for my own use. But the literal example that we're going to go over now is sort of this different agent supervisor architecture that I have. And so I've done my best to sort of graph it out here. And what's sort of going to happen is we're going to have the user, that's us, give an input to a original supervisor agent. And the supervisor agent isn't actually going to generate anything at all. It's just going to route the work and manage a conversation almost between these two sub-agents. We're going to have an analysis agent and a writer agent that is working for the supervisor agent to give the output finally to me, the user. Within the sub-agents, we've got the analysis agent, and the analysis agent is going to have tools available to it. So the agent itself is going to be a large language model, but that language model itself isn't necessarily going to actually generate anything. It's going to use the tools available to it, this sentiment analysis tool and emotion analysis tool that I have, to actually do that generation before giving the output back to the supervisor agent. Similarly, over on the right here, we've got the writer agent that will have a report generating tool and a report revision tool. And of course, this is all sort of an approach to social media sentiment analysis, which tends to be a good sort of example that I've been using when putting together different agent architectures and artificial intelligence applications. And also, one of the things that you might see is that these tools aren't anything that we have actually gone over. Things like Tavili search or, web search or looking at stuff like that. These are all ones that I've defined myself. And funnily enough, within them, they're also large language models that are being the tools. So in essence, what we're going to have is almost a manager, GPT-4 Turbo here as the supervisor agent, with two sub-workers that are an analysis agent, the writer agent, that are both large language models that have sub-language model tools, which are just going to be one-shot calls to the OpenAI API with the different models that actually create the sort of content for them that they shove back in to the user. So let's go over the code now and see how this actually pans out. A quick note as well, we're going to be taking advantage of LangChain's application LangSmith, which is a phenomenal tracing program that they have that's really great and pretty crucial, I would say, for actually debugging and seeing sort of the behind the scenes of how these agent architectures interact with each other, respond, and output. And so we'll go into what that looks like sort of at the end when this actually runs, but let's move on to tools. And so the tools here are pretty simply, as you can see, a simple setup with LangChain Common Expression Language to do emotion analysis with my fine-tuned model. And if you haven't seen that video, go ahead and check that out to see how I get these fine-tuned models. And then you can actually use a tool decorator that LangGraph provides to attach it to pretty much any sort of function that you define to turn it into a usable tool for an agent. So this setup is simply just having the prompt, running it through a prompt chain to call the model, And then I shove that into a super, super small analyze emotion tool here. That's just a function that has, it's going to expect a string in and it's going to expect a string out. You then have to put a sort of explanation of what this does, and then it's simply just invoking the LangChain chain to get that query from the string query in. And so the few necessary things that you're going to have here is this tool decorator, which is what the LangGraph package can actually, take these functions and then convert them into the correct sort of format behind the scenes for tool calling. And then you also need to specify sort of your inputs and outputs, since that is going to be crucial for the language model to actually understand what it needs to input and what it expects to get out. And then also, well, I know a lot of people don't tend to sort of put this triple quotation explanation of what a function does in real practice. This is actually what the language models are going to be able to look at to see what the tools do. So this is just me defining a tool, and it can really, as you can see, be any sort of function. Things like, calling a different API to search the web. Things like calling maybe an API to do math equations. Literally anything to your heart's desire, as long as you set it up like this and add a little tool decorator and make it, easy enough for a language model to input and output, you can have it be a tool. And so going through, as I mentioned before, all of my tools are actually just going to be similar calls to sort of OpenAI with different language models to do different things. And so we go through here, and I've got one for, writing a report. I have just another thing here that will save the report as an intermediary step when generating it, and then also revision tool here. So tool definition can be whatever your heart desires, as long as you take this, simple sort of approach of making sure you explicitly define what its purpose is and its inputs and outputs. Then we get into the fun part of actually creating the agents. So the agents, of course, aren't going to be as simple as just, having a prompt, making a chain, and then invoking it like these tools are. We're actually going to need a few more things. So within this, you can see I've got a couple helper functions, which later we'll call to actually define the agents, but it takes a chat OpenAI LangChain object as the LLM. You give it a list of tools, which are defined with the tool decorators here, and then you can also provide a system prompt. The system prompt, of course, is going to be very necessary for strictly defining what the agent is actually able to do. Then it has a couple things of message placeholders. And these message placeholders are really crucial because the messages are actually going to be sort of the logged history of the outputs and the different inputs that each agent is making. And so you're going to want to use this as sort of a pseudo memory to allow the agent to see what's been done and who's talked to who and what's actually happening. And then the agent scratchpad is also going to be acting as a memory for the agent to sort of put messages in itself so that it can actually, reason through, work through a problem. And then if it needs to do multiple sort of steps before returning an output, it can write it down here on the scratchpad, where it's then sort of converted into this overarching state and overarching message that's passed between the different nodes in this LangGraph agent ecosystem. They have this great function, the create OpenAI tools agent, which you can just pass in all of these things to create the agent. And then LangChain has an agent executor, which allows you to invoke an agent similar to how you would invoke a LangChain chain. The agent node here is just going to be sort of a way to actually do the invoking of the agent and then returning its output as sort of a human message. Because now with different language models talking to each other, the way that it has is it requires a system message, a system prompt, an AI message, and a human message. So if we take this AI output message, just put it back into the sort of format of a human message, you can re-input it into another LLM as that input message. And it just sort of just takes that as sort of the human message input that you would usually do as a user. And so, of course, according to our architecture here, we're going to have to make the manager, the boss here of the agents. So we first define sort of the main agent supervisor. And I go through this pretty much step by step, not using any of the helper functions. This is all pretty much made from scratch. So I first define the members here. We're going to be using the analyzer and the writer as the sub-agent. We also define a system prompt. You are a supervisor tasked with managing a conversation between the following workers. And then we're going to dynamically input with this partial down here when we get to it, the actual members, which are the analyzer and the writer, giving the following user's request. Respond with the worker to act next. Each worker will perform a task and respond with their results and status. When finished, respond with finish. So in short, we're pretty much giving it the option to either say the analyzer, the writer, or finish. And then we take this and shove it into a function that we're going to be calling next. So it's going to be using this in sort of the OpenAI function calling to make the output that it actually gets a little bit easier for us to parse in the back end. But then also, when you sort of put it all together, pretty much all that this main supervisor agent is going to do is it's going to take a look at the user input. It's then going to just route. It's going to say either this needs to go to the analyzer, this needs to go to the writer, or it's finished as is. And then it's going to shove it into, whichever sort of sub agent it thinks it's going to be. The sub agent is then going to produce its output, give it back to the supervisor. It's going to take a look at that, manage this quote unquote conversation that's happening, and then say whether it needs to go back to sort of say the analyzer, back to the writer, or if it's finished, it sort of ends the state and gives the final output to the user. And so using this, we use, as I said, OpenAI's function calling sort of schema here to actually make this a little bit easier for us to parse in the back end. We then have a prompt from a simple chat prompt template with the system prompt and a messages placeholder. And then we partial sort of this function to actually be able to dynamically input things like members into this actual prompt. The LLM is then going to be GPT-4 Turbo, and then we put it all into a supervisor chain. The big things here is that we're taking this prompt that we're making, we're binding functions to the LLM. So the bind functions method here is what actually formats our tools into the right format so that the LLM knows that it has tools available for it to use. And then we're going to just be using a JSON output functions parser from LangChain so that all of this goes a little bit nicely and a little bit more easily. And so then we're going to be using the LangGraph package to actually create this graph, or how these agents can actually talk to each other, what information is going to be able to be passed to and from each other, and sort of how this overarching logic is going to work. So to go over, I've put a little bit of definitions here of what's actually happening in the code before we go down. We have this class, which is a typed dictionary that has the ability to create annotated messages with an operator.add. And what this basically does is it defines the structure of the state that will be passed between the agents in the system. Base message operators are added in sequence, which effectively tracks sort of the workflow as an ongoing conversation or data exchange between these agents. Next, which we have here as a string, specifies the next agent or node in the workflow to route this process and pass this state to. We then set up some LLMs here, and we use our helper functions, the create agent, to actually pass in the LLM, a list of the tools that are available, and then a system prompt. We then use the partial on the agent node to put together this as a node in our graph, which we have here, yes, agent node. So what that means is that we're not going to have to define the agent or the name later. All we can do is call this analysis node with the actual state, because that's the only thing that we didn't specify with this partial function operator. And so we do this with a couple of them, and the analysis and the writer agent. And what this basically is doing is, an instance of GPT-4 Turbo is made, then the helper function is invoked with the LLM object, a list of the tools it intends to use. For the analysis agent, that's the analyze emotions and analyze sentiment tools, a system prompt, and then the node uses the partial function of agent node with the agent and name preset. So the node only needs to take in the state as defined by the helper function agent node above. So that's great. We've made the agents, we've defined the nodes from the agents, and then we put it all into a workflow. So for the workflow here, we have a state graph that's initialized with the agent state class structure that we have above here. And this graph sort of represents the entire workflow of the system, where nodes represent agents and edges represent the possible transitions based on the agent's outputs. Nodes are added with the add node function using the above defined nodes and a name, with the supervisor node being the above defined chain. So basically, all of these nodes just mean we're adding in the agents. The agents are going to be represented as nodes on this state graph with the class agent state here. We then have to define how they talk to each other with the defining edges section here. And so edges basically define the logic of which node or which agent can actually communicate with the others. The initial for loop that we have here for member and members, workflow.addEdge member supervisor, this connects all of the members to the supervisor node, as they will all need to sort of report back to the supervisor when finished for a supervisor and sub-agent architecture that we have defined at the top of the notebook. Conditional edges here are set up first using a conditional map. That's this K to K for K and members, which is basically just going to be a dictionary created with the keys from members and an additional key for finish. Each member of this map is going to be mapped to itself, meaning that if the next field in the graph state indicates a member's name, the workflow will route to that member's node. The finish key then maps to end, which terminates this agent loop. We put it all together with this lambda function of adding conditional edges, and we add the edges to the supervisor node that are conditional based on the value of next. So the lambda function extracts the next field from the state, and the conditional map is used to then determine the target node based on the value. If next is a member's name in the workflow, it routes to that member. If it's finished, the workflow ends. And so this takes a little bit, and I certainly recommend practicing to actually get sort of, this hypothetical way of thinking about these agents as sort of dots on a graph almost and connections to it. So definitely, check this out, try it yourself, try different architectures yourself to fully understand this, and check out LangChain's other documentation on this stuff, because it would, they go into a much better detail of how this is set up. This is more of an overarching analysis. But finally, what we do is we create the graph with workflow.compile. And so it's all done, everything's set up, and internally it will look basically like this, where the agent can route to either one of these. The output's only going to go back to the supervisor agent, and then the supervisor agent is going to be doing that sort of next routing. And so then it's ready to try out. So let me show you this example that I tried it out with. Of course, since this is social media comment analysis, I have this JSON, which I really don't like the way that Jupyter Notebook displays JSONs, but it's basically just indexed 0 to 10, so 11 full comments of these classic comments that we've seen before in some of the other videos around social media sentiment analysis and other things that I've done with these. So similar data set, I've only grabbed 11 to see what it would do. But I basically path to it, open it up as comments, and then I'm actually using streaming here so that we can see sort of the different things that are going on behind the scenes. And I input only, first perform a robust analysis, and then secondly, write up a report on these social media comments. So as you can see, very, very basic prompting that we have here. I'm just giving it the file, which is all these comments, and then asking it to perform analysis and write up a report. So nothing too crazy, not a huge prompt at all. It's all going to be executed behind the scenes with all of the logic being, executed from the language model itself. And so to actually see what's happening behind the scenes here, we're going to hop over to LangSmith, which is LangChain's tracing service, where you can actually see sort of what's happening, what's being called, who's saying what behind the scenes. So we can see that overarchingly, this is what I input. So, perform the robust analysis, yada, yada, yada. And then it's just going to be a plain sort of JSON input of all of these things. And then we can see the output here of what it was formatted into. We see that this is then routed to the supervisor. So if we hop over to the supervisor, all it does is it takes a look at this and says, what do I need to do? So I need to route this to the analyzer. And we can see that's exactly what it says. So it says analyzer, which in our logic means it's going to hop over to the analyzer. And so then hopping over to the analyzer here, we see that it takes this, so it takes this, which the supervisor had given it, and then we can see over here that these wrenches actually represent tools. So we can see that it's calling analyze emotion, analyze sentiment, analyze emotion, analyze sentiment. And if we dig into one of these, you can see that it's just taking one of the queries, one of the comments, and then running it through this actual tool. And so the tools that we defined earlier, like sentiment and emotion, we're seeing that it's returning back, neutral for these. Maybe we'll get something a little bit different. Oh, this one is negative here. And it goes through and runs all of these tools. So it understands that it has these tools available to it and is going to be using them to create its final output. And this is great. This is exactly what we want to see. And this is, of course, with no sort of explicit logic defined by us. This is purely the language model in this sort of agent state reasoning that it should be using these tools to create the final output. And so then finally, if we hop down here, we can see that using that, it combines it all into this quick sort of, there's a little bit of key findings and conclusions that it adds onto there, but it's not the writer. It's not supposed to be doing that. It pretty much just puts in the emotion and the sentiment for each one of these here, which is great. This is exactly what the analyzer should be doing. Since it's finished up doing that, it knows that it needs to return its output. And where does its output go? It goes right back to the supervisor. So the supervisor takes this, as we saw, as a human message and sees this report that it generated. And the supervisor goes, okay, great, we've got an analysis report. Let's now route that to the writer. Phenomenal. So it says writer here. And then with that conditional edge logic that we put in, it spits it all back to the writer. So the writer over here sees two messages. It sees the human message where we input all of this, and then it sees the additional human message where the analyzer actually put out this. And then the output, well, it doesn't put it here, but it uses this tool then, the generate report tool, to actually create that final report. So this is the final report that it puts out, and then it doesn't actually choose to use the revision tool. So that's something also that we're seeing here with this sort of undefined logic, is that it thinks that this report is, good enough. So then it routes it back out to the supervisor. The supervisor then sees that it's got three messages. We see that the human wrote this. We see that the analyzer gave this analysis. We see that the writer has generated a report, which we've saved with the tool function. And then it says, great, that's finished. And then it says finish, and the entire agent chain ends. And so this took about 277 seconds, cost about 18,000 tokens to put this through. But it's super interesting to see now that it's actually more of a conversation with a manager of different workers almost going through. And then you can see its sort of internal memory of understanding what the messages have actually been, and then using these different tools to sort of fully route and reason of what it should use to get this final output. Taking a look back at the notebook then, we can see sort of this general flow that we streamed out here. We see that it goes to the analyzer from the supervisor. Analyzer does this, shoves it to the writer generates the report, and then it says finish. So it's not as detailed as the sort of LangSmith run that we just went over here, but this is sort of what's going on too that you can have. And so then this is what the final report looks like. So it's exactly what I was sort of asking it to do, and it was able to reason through, use the tools at hand to create and sort of output this final report. And of course, I've got this LangSmith run trace linked here in the bottom of the code, which you'll be able to see. And of course, all of the code is going to be linked down there as well. And so to add some sort of conclusion to this, agents I do feel really are a natural progression in allowing language models to do things like reasoning, simulate human thought and actions a little bit better, and then also making them a lot more useful. Not just having them be sort of that final ambiguous output, but being able to define explicit tools for use. And we're seeing a lot of AI agents now actually pop up. Ooh, that's a little bit too much. Pop up here. Things like closed source, open source, all sorts of them. Open Devin is one that's been trying to sort of recreate Devin in an open source way, but it's a little bit in its infancy right now, which is super exciting, of course, because we get to see all of this innovation go on with language models as they sort of progress in their usefulness, really. And so at its core, I'm going to go back to this, very simple graph from NVIDIA that talks about agents. And to provide some sort of final definition on agents, it's really using the language model as sort of that operating intelligence system, providing it with sort of a way to keep track of its memory, providing it with a way to reason and sort of use its reasoning abilities of its emergent properties to plan what it needs to do, and then explicitly defining tools that it can use to sort of create all of its output for the end user request. Of course, the one major downside with this, which you can probably tell from the LangSmith run costing 18,000 tokens, is that to do all this, it requires a lot and a lot of compute, a lot, especially if your memory and your messages are getting long, or if you have lots and lots of agents. Sometimes you might even add another supervisor agent above this architecture that has a sub supervisor agent that has sub agents that has tools. It can get really expensive, really token heavy, really quick. But super cool, super exciting time to be experimenting with, automating sort of these workflows with language models and artificial intelligence. So hope that provided a great overview of sort of this infancy of agents and how they're coming out right now, and also some good examples. So I have a lot more resources linked in the description below, especially a link to the code so that you can check it out, try stuff yourself, use exactly what I was using. And then also, if you like stuff like this, feel free to check out my other videos, drop a comment if you got any questions, and of course, make sure to subscribe if you're enjoying it.